I hope everybody is doing fine, and in this video I'll be talking about digital to analog converter. It is generally symbolized as DAC. So the title itself suggests us that you're going to have the input as a digital in terms of zeros and ones, and you are transforming this digital uh, uh, energy into the analog output. So this DAC it converts a digital input signal into an analog output signal. So to say, the digital signal is represented by what I said already, by the binary codes, which are basically the combination of zeros and ones, what you call on, off, high, low. So in binary system we have two kinds of formats. Now this is what we are going to deal that using operational amplifiers we can have we can convert these digital signals into the analog signals. So if I have to symbolize it, so this will be the right way to do it. Here we have a DAC, and DAC is digital to analog converter, and we have input for it, and we have output. So input is digital, so that's an important thing, and the output is analog. Output is analog in nature. So this is how we can start with, and a, a digital to analog converter. It consists of number of binary inputs, right? And it has single output. That should be kept in mind. In general, we have uh, a range of binary inputs of this DAC uh, in the powers of 2. And now these DACs, there are two types of DACs. One is called weighted resistor. One is called weighted resistor, DAC. And the next one is called as R-2R, ladder, DAC. So the job of these two is to convert these digital binary numbers into an analog output. Now let us start discussing this weighted resistor DAC. So now to introduce you with this weighted resistor DAC, uh, a weighted uh, uh, a weighted resistor DAC produces an analog output, which is almost equal to the digital binary input by using binary weighted resistors. So the mode in which these operations are carried out is in the inverting adder circuit. I think we have already discussed uh, the application of operational amplifier as adder. So this job is carried out by virtue of making use of this inverting adder circuit. So, in short, if I have to shorten this discussion, a binary weighted resistor DAC is called as weighted resistor DAC. So, binary weighted DAC, right? Uh, and we call it as weighted resistor DAC. Now let's go with the right thing here would be to go with the circuit diagram and then analyze that circuit diagram. And there we can have long different ranges of combinations that can be used in designing a DAC. Here, what we will do for the sake of simplicity, we will make use of 3-bit binary weighted resistors, right? So to start with, we have an operational amplifier like this. This is its inverting terminal. This is its non-inverting terminal. This is the output, and here I have a feedback resistance, and this is the non-inverting terminal. This is grounded, and then we have a network, a network of resistors. Let me take it down like this, and let me have because I'm talking about 3-bit binary weighted resistors. So I will be choosing 3 resistors. Say this is resistor 1 and this is resistor 2 and this is resistor 3. And let me keep them like this, and let me have a negative ground, what I will call as minus VR, that uh, available to these resistors. Now here I have a ground. Okay, I can think of a ground here. I can think of a ground here, and I can think of a ground here. Now, what's the combination here is that here, if I start from here, this will be 2 to the power 0R. This will be 2 to the power 1R, and this will be 2 to the power 2R, right? So this is the situation. We have a DAC, and this DAC should perform a job where it will convert the binary signals, 3-bit binary signals, into a single analog output. And obviously you can think in terms of the virtual ground and virtual short. We have discussed these things many a times in past. So let's go and analyze this circuit and see what are the outcomes of this circuit. So if you recall that the bits of a binary number can have only one of the two values, as I told in the beginning, right? It can be either 0 or it can be 1. Now let us assume this 3-bit binary input in the form of some bits like B1, B2, and B0. I mean, let's have these things like B2, B1, and B0. So these are the 3 bits that we assume as the input for these uh, three resistors, right? So B2 should be linked with this, and this should be B1, and this should be B0. This should be the case, and uh, and let this B0, let this B0 denote MSB, and MSB is what? It is the most significant bit. This is most significant bit, and this B2, this B2 should be as the least significant bit. All right, so let's move on from here. Now, what's the purpose here? I mean, we have the digital switches here shown in this figure, and and they will be connected to ground when the corresponding input bits are equal to 0. So the condition is here: for 0, this thing will be connected to ground, right? And for 1, this thing will not be in touch with the ground. So similarly, the digital switch shown in the above in the given figure will be connected to the negative reference here. You can see here it will be connected to the negative reference here when the corresponding input bits are equal to 1. Now, in this given circuit, the non-inverting input terminal of an operational amplifier is connected to the ground. That means 0 volt is applied at this non-inverting input terminal. So now here we can think in terms of the virtual ground. Now, according to virtual short concept, which we have already discussed, according to that concept, what we are going to get here, if we have potential here equal to 0, right, at this terminal. See, this non-inverting terminal is grounded. So if it is grounded, we will have 0 voltage here. Now, if we have 0 voltage at this point, we can immediately think of 0 voltage at this terminal by virtue of virtual ground concept. So this is my junction. You can think of this junction as P, and you can start. So this is my feedback resistance, or F, and we can immediately think in terms of nodal equation, or what we call as the equation which comes out by virtue of exploiting a junction. So when we'll do that, we will have a nodal equation for this. For this circuit, and what will that equation be? And we can see here that we have the feedback resistance here, and we have the arrangement of these resistors into the powers of 0, 1, and 2, and the bases are 2 in every case, because we are talking about bits in this situation. So to proceed from here, what can we expect is a nodal equation of at this point P, and if you start from the V out, if you start from there, we can immediately take on 0 plus VR B2 by 2 to the power of 0 plus 0 plus VR B1 divided by 2 to the power of 1. Here I must have R. Plus 0 plus VR B0 divided by 2 to the power of 2R, okay, is equal to V out by RF. This will be the result of evaluating this junction in terms of currents, and that can be done in a very easy way. That's not going to be the big task. We can understand that. Okay, so we have a nodal equation here. So let us go for some approximations here. So what's going to happen here is I have V out by RF. So this is VR B2 divided by 2 to the power of 0 R plus VR B1 2 to the power of 1 R plus VR B0 to the power of 2R. This is the situation here, right? And we can have things out from this equation. Say this is V out by RF is, I think VR is same for everybody, and RF is, this is RF, this RF, where is it? This is RF is here. Okay, so here I have VR out, and I think I should go with R. Okay, so I will start my bracket. This is B2 by 2 to the power of 0 plus B1 by 2 to the power of 1 plus B0 2 to the power of 2. So immediately we can take this RF to this position, right? And if we go with an approximation that R is equal to 2 times RF. If we go with this assumption, so this RF will come here, and we will see what's going to happen. Okay, so after this we have, so I will write here V out. So V out will be it will be VR, okay, then RF, okay, RF, I'm taking this RF here, and for R I will use twice RF times B2 by 2 to the power of 0 plus B1 by 2 to the power of 1 plus B0 by 2 to the power of 2. Right? So this is it. Now we will have the cancellation, right? And this RF will be cancelled with this RF. So what will be my V out? It will be VR times B2 by 2 to the power of 0 plus B1 by 2 to the power of 1 plus B0 by 2 to the power of 2. So this equation represents the output voltage equation of a 3-bit binary weighted resistor. And since the number of bits are 3, so if you think of 3 bits, 0, 0, 0, right? So then you can have a configuration of 7 possible values of output voltage, because you can range these zeros as say 0, 0, 1, and you can range it up to 1, 1, 1. So there will be seven different modes that can be executed using this formulation. And we can generalize this output voltage. We can generalize this output voltage for n bit, for n bit binary weighted output voltage. So that's the case, right? And what will be that equation? How can I generalize that? How should I write this equation? Is I should say this V out is VR by 2 is okay here. Then it is Bn minus 1. So let me take this as capital. Divide by 2 to the power of 0 plus Bn minus 2 divide by 2 to the power of 1 plus so on so forth, B0 by 2 to the power of n minus 1. So this will be the generalized output that we can expect from this DAC by making use of the analysis that we have carried out. Now to proceed, now this kind of configuration that we have discussed is that in this case, the difference between the resistance values corresponding to LSB and MSB will increase as the number of bits present in the digital input increases. So this is going to be the problem. Therefore, it is difficult to design more accurate resistors as the number of bits present in the digital input increases. So this can be taken as the disadvantage of this this kind of DAC. Now, the next one is R-2R ladder DAC. I mean, so this is 5. The next one is R-2R ladder DAC, digital to analog converter. Now, what is so great about it is that this R-2R ladder DAC, it overcomes the disadvantages of binary weighted resistors. The binary weighted resistors DAC. As its name suggests, I mean, it is R-2R ladder DAC. It produces an analog output which is almost equal to the digital binary input by using R-2R ladder network. So there is a sophisticated ladder network that's used where the precision is great, where the precision is very good. So the same analysis we would like to have here. We would like to go with the circuit diagram of a circuit diagram for this 3-bit R-2R ladder DAC. So to go with it, we have as usual, we have the operational amplifier. All right, so minus plus, and we have the output, and we have a resistance R here, and here we have a resistance 2R. So, okay, then what we are going to do is we will have a network here. Now this is my resistance. This is my resistance, and here is my resistance, and here is my resistance. Okay, uh, here I have another resistance, and here I have another resistance. To make it consistent, I should cut it here, and I should go like this. Okay, so here I will, there's nothing here. Okay, nothing. Okay, so now it's consistent here. Okay, we have a resistance R here, we have a resistance R here, and here we have 2R. Here we have 2R, and here we have 2R, and here we have 2R. So in every case we have a ground. We have a ground available. We have a ground available in every case. We have a ground available in every case, and we have minus VR. Okay, so this is the circuit diagram for R-2R ladder digital to analog converter. Now, if we go back to the concept of the bits of a binary number can have only one of the two values, right? It can either be 0 or it can be 1. Now let us assume that the 3-bit binary input that we have here is B2, B1, and B0. So let's go with the same thing here is B2, B1, and B0. All right. So here these B2, B0, they denote this one is the MSB, and this one is the LSB, right? So most significant one, and this is the most significant bit, and this is the least significant bit. Now, the digital switches that we have shown here, okay, they will be connected to the ground when the corresponding input bits are equal to 0. Similarly, the digital switches will be connected to the negative reference voltage minus VR when the corresponding input bits are equal to 1. Right? So these are the connections that will be used either to be grounded for the 0 case or to be connected to minus VR voltage. It is basically very difficult to get the generalized output voltage equation for this R-2R ladder digital to analog converter, but we can find the analog output voltage values of R-2R ladder for individual binary input combinations easily. So the advantage of this R-2R ladder DAC are like that. This R-2R ladder DAC contains only two values of resistors, and for that we have R and 2R. So it is easy to select and design more accurate resistors. If more number of bits are present in the digital input, then we have to include the required number of R-2R sections additionally. So that way, this R-2R ladder technique becomes beautiful, it becomes feasible, and it's capable of doing the job. Now, these because of these advantages, this R-2R ladder DAC is preferable over binary weighted resistors. So the rest you can do yourself. You can analyze those binary parts, and you can develop the nodal equations, wherefrom you can calculate the output of this R-to-R ladder digital to analog converter. So bye, goodbye, have a good time.